We already know that when we want to compare means across two populations, we can use t-procedures to test for significant differences. However, t-tests are not very helpful when we have more than two groups. You may say that we could compare two groups at a time and then draw a conclusion about the differences between all of them. From a statistical point of view, the procedure would be very inappropriate. The main reason is that if we do this, the probability of type 1 error from every comparison accumulates to a total called family-wise error, which is much greater than the error for one single test. So the overall probability of type 1 error increases with every new comparison. The solution to this problem is to use another method of comparison, which is called analysis of variance, and is most often abbreviated ANOVA. This method allows us to compare many groups simultaneously. Furthermore, ANOVA analyzes the variance. This is where the name comes from. The variance, or how spread apart individuals are within each group, as well as between the different groups. There are many types of analysis of variance. In this presentation, we will discuss the simplest type of ANOVA, which is called a one-way ANOVA. This example illustrates how to conduct a one-way analysis of variance to compare mean differences across three different groups. Let's say that a group of researchers would like to determine which method of instruction is most effective, face-to-face, online, or hybrid, which includes both face-to-face meetings and online sessions. To investigate this, researchers randomly assign the participants in the study to one of the three cohorts. These individuals have similar levels of background knowledge on the topic and take exactly the same course from the same instructor. The only thing that differs across the three groups is the way instruction was delivered. At the end of the course, all students take an achievement test, the same test, to measure the extent to which they master the course objectives. The null hypothesis here is that there is no significant difference in average test scores across the three groups. The alternative hypothesis for ANOVA is always multidirectional because means may vary in both directions, and these variations may occur for each one of the three groups included in the analysis. When we conduct statistical analysis involving multiple comparisons, there are two main steps that we have to take. First, we must conduct a test of significance to determine whether the differences between means are statistically significant. This involves computing a test statistic and finding a p-value. The test statistic for ANOVA is called F. Second, if the null hypothesis is rejected, we must find out where the significant differences occur, because some means may be very similar, whereas others may be very different, significantly different. When we conduct ANOVAs, we are comparing means, but we are also taking into account the variability of scores within each group as well as across groups. When the separation between groups is very clear, the means of these groups are far apart, and the scores recorded by the individuals who belong to different groups are also far apart, while the scores of individuals within the same groups are very close. For instance, the three box plots on the left side show that these three groups have different medians, but the spread of each group is quite large. There is a lot of overlap between the three boxes. Therefore, the distinction between groups is not very clear, or there is a lot of error involved when we look at the differences between these groups. The example on the right shows three groups that have the same medians as the groups on the left, but the distribution of scores within each one of these groups is much more compact. Scores within each group are not so spread out. Therefore, there is a more clear distinction between these three groups, or less error. For our example, we can use software to run some descriptive analysis for the test scores obtained by the students in our three groups. When we use statistical software to run ANOVAs, a table of descriptives like this one is included in the output. However, it is always a good idea to look at the descriptive statistics before conducting the analysis. In our case, we can see that students in the hybrid cohort had the highest average score, followed by the online cohort and the face-to-face cohort. Face-to-face instruction is labeled as traditional instruction in this dataset. If we take a look at the box plots, we can see that the hybrid group has the highest median, but also has the largest spread. Both the box and the whiskers are longer, so there is a lot more variability in scores compared to the other two groups. This information is taken into account when computing the ANOVA test statistic. The question is, are the differences between these three means statistically significant? To answer this question, we must compute the test statistic. The general formula for computing the test statistic is a ratio of the variation of scores between the different groups and the variation of scores within the groups. The computation process for the F statistic is a little more tedious than for the Z or the T test statistics. It can be computed by hand, but the computation involves many steps, and any statistical software can compute the F statistic for us. The important thing is just to understand its meaning. The F statistic always takes positive values, because these variances are actually means of squares divided by the degrees of freedom, and none of these terms can take negative values. Just like with other test statistics, large values indicate large differences between groups, so the larger the F statistic, the more likely it is to have a small p-value and to reject the null hypothesis. When conducting analysis of variance, sample sizes are also important. The larger the sample size, the larger the F statistic, and therefore the more likely it is to have findings that are statistically significant. In contrast, the larger the number of groups, the smaller the test statistic. Because ANOVA compares individuals both within groups and between groups, we have a within group DF, which is equal to the sample size minus the number of groups, and we also have a between groups DF, which is computed as the number of groups minus 1. And we also have a total DF, which is obtained simply by subtracting 1 from the sample size. You do not have to compute these yourselves, but it is important to know where these numbers are coming from when you're interpreting the output from statistical software. In our example, we have a sample of 75 students in 3 groups, so we should see in the computer output a DF of 72 for the within group comparisons, a DF of 2 for between group comparisons, and a total DF of 74. The next step we have to take is to run the statistical analysis and to interpret the results. The first column in this table, labeled Sum of Squares, shows the sum of score variances between and within groups, as well as the total sum for the entire sample. We also have a column for the degrees of freedom that we computed earlier for each type of comparison and for the total sample. The mean square column shows the average variation of scores between groups and within each group. These values are actually obtained by dividing the values in the sum of squares column by the corresponding degrees of freedom. The within group variance is also called error because we want groups to be as homogeneous as possible, so variation within groups brings error in the computation process. The F statistic is a ratio of the between groups mean square and the within groups mean square. So if we divide 1087 by 15, we get approximately 7. All we have to report from this table is the value of the F test statistic, the degrees of freedom, and the p-value. The APA convention is to write the degrees of freedom in parentheses next to F. For this example, the test statistic F with 74 degrees of freedom is 7.21 with a p-value of 0.001. Because this p-value is lower than alpha of 0.05, we can reject the null hypothesis and accept the alternative hypothesis. So now we know that there is a significant difference in student performance across the three groups. However, because we compared all groups simultaneously, we cannot tell where the significant differences occur. Are all group differences significant or only some of them? If and only if the F statistic is significant, we can conduct some follow-up analysis to determine which groups have means that are significantly different and which don't. These are called post hoc analysis, and there are a variety of tests that we could use. The simplest one is called the two-key post hoc test, or the two-key procedure. With this procedure, for each group, a difference is computed between the average of that group and the average of every other group, and these differences are tested for statistical significance. This is the output table that reports such differences and the results of the tests of significance. The first column of the table shows the first term of the subtraction, and the second column shows the second term of the subtraction. For instance, the first row is for the difference between online instruction and hybrid instruction, while the second row is for online instruction minus traditional instruction, face-to-face instruction, and so on. Mean differences between groups are reported in the second column of the table. The differences that are statistically significant have an asterisk next to them. In our example, we can see that the difference between hybrid instruction and traditional instruction is the only one that is statistically significant. Of course, the difference between the average for the traditional instruction and the average for the hybrid instruction is also marked as statistically significant because it is actually the same difference, only in the inverse direction. The other two differences, online minus hybrid and traditional minus online, were not statistically significant. Another thing that the two-key procedure does is to group the averages that are similar into clusters or subsets. We can see in this table that the traditional and the online instruction were grouped into the first subset because they have means that are close and not significantly different. Similarly, on the other end, online and hybrid instruction were grouped into subset because they have means that are close and not significantly different. The only two means that belong to two different subsets are the means for traditional and hybrid instruction, which were significantly different. Therefore, we can conclude that students in the hybrid course had the highest test score, followed by the students who took the online course and the students who attended the face-to-face course. The difference between hybrid instruction and traditional instruction was statistically significant, whereas the difference between hybrid and online instruction and the difference between online and traditional instruction were not statistically significant. There are certain assumptions that we have to meet when conducting analysis of variance. The first one is that the samples are independent, that the individuals in each group are completely unrelated and were selected at random. The second assumption is that the variable we're testing has a normal distribution in the population. Typically, a distribution that is single-peaked and relatively symmetric will suffice, especially if the sample is large. Another assumption is that the population standard deviation of this variable is the same across the compared samples.